Yeah, welcome to this talk. My name is Bo. I'm a principal engineer at Katana Graph. Today I'll talk about the system we are building for high performance and unified graph computing and how it is used for large-scale GNN workloads. I'd also like to share some experiences we learned from our customers and real-world use cases. This is the outline of this presentation. I'll talk about Katana Graph AI platform and how a large-scale graph machine learning pipeline uses its key components. Then I'll briefly describe how the system performs pre-processing and feature engineering. After that, I'll talk about the mini-batch training support, which is the most popular way to train GNNs on very large graphs. Then I'll describe a use case where graph querying is used to prepare training datasets for a graph machine learning model at a pharma company. I'll conclude the talk with several takeaways. Graph AI has attracted significant attention in the past few years. There are multiple systems like DGL and PyTorch Geometric for users to easily train GNNs on small graphs that fit in one single machine. However, real-world graphs are huge. They are massive. They may have billions of nodes and trillions of edges. So naturally, an enterprise-level graph AI system should be able to leverage a cluster of machines to handle such massive datasets. Many challenges arise because users prefer a simple abstraction. For example, most users do not care about how the graph is partitioned and distributed. And they want to use familiar interfaces in Python to specify GNN architectures. They may also want to run graph queries to extract subgraphs of interest and then run graph algorithms like clustering or PageRank to featureize the data. So the goal of our system is to address these challenges and provide the users with a notebook front end, very easy to use. So they can just use a simple Python-based abstraction to run very large graph AI workloads on a cluster. In the middle of this figure shows the core of the Katana system, which is designed to handle general or large-scale graph computing workloads. We designed a graph storage format called Resilient Distributed Graph, or RDG for short, with efficient in-memory topology and property data representation. Our scalable distributed graph engine consists of three components: a streaming partitioner, a parallel graph compute engine, and the distributed communication engine. The system has a bunch of ETL tools to convert raw data into RDGs and ingest RDGs from AWS, Azure, or GCP. Our compute engine can also leverage heterogeneous computing resources like GPUs. So based on this powerful engine, we implemented multiple graph libraries for graph querying, analytics, mining, AI, and machine learning. I'll briefly go over the components in the core engine. The efficient graph representation is challenging because graph data is heterogeneous, dynamic, and massive. Our RDG format is essentially a collection of versioned partitioned views of a distributed graph. It's important that the views are optimized for target applications and the graphs, and they can be managed automatically. So for example, if a graph has a non-trivial number of high-degree nodes, then a vertex cut partitioning policy works better than an edge cut partitioning policy at balancing distributed workloads. Then we can create a partition view for the graph with a vertex cut partitioning policy. In contrast, for a graph with a more even degree distribution, it may make more sense to generate a view with an edge cut partitioning policy. If we zoom into a view, we will see that it has metadata about the graph, like when it's created, The topology of each partition are represented in the CSR format, compressed sparse row format, as well as node and edge properties in the columnar representation. The entire view can be stored in Parquet files and can be repartitioned when the users want to use more machines, for example, to improve the throughput. The partitioner is a critical component to support large-scale graph computing because it's a key player in the first step to distribute data. The partitioning process can incur huge costs for large graphs. So to address this problem, we implemented a streaming partitioner. In just one pass of the data, the partitioner can leverage different partitioning policies to determine where to place the edges. What it enforces is that each edge is assigned to a unique host. However, the problem is that multiple edges may involve the same node, and thus that nodes may appear in multiple machines. For example, this figure in the middle shows that node C appears in both machines because it appears in two different edges. Then the partitioner creates two replicas, one on each machine. It then chooses one of these replicas as a master replica and the other as a mirror replica. We also make sure that each machine has up to one replica for any node. So this streaming partitioner turns out to be quite efficient and can process very large data sets in a distributed and streaming manner. Our communication engine leverages round-based bulk synchronous parallel processing. At the end of each round, master replicas are updated by aggregating information from mirror replicas if needed. The communication is optimized to be partition aware. For example, if a node's neighbors are all scattered on two machines, then this node's host only needs to communicate with those two machines. So that can increase the communication efficiency. Then for aggregation or reduction, the system supports different distributed accumulators like max, min, average, and so on. We hide the implementation details and provide intuitive interfaces in both C++ and Python. So the communication is used in all the graph workloads. The communication engine is used in all graph workloads, including querying, analytics, and graph machine learning. We believe that practical large-scale graph machine learning needs all the components I talked about. Essentially, the pipeline should be graph data centric. The system should be not only concerned about GNN training, but also graph data manipulation and analytics. The pipeline should contain at least 4 stages. The first stage is the graph preprocessing stage. So it partitions the graph and may rewire the graph if necessary. So the second stage is graph feature engineering. We know that most graph data don't have initial vector features. Instead, the nodes and edges in the graph have properties. So graph feature engineering encodes the properties into initial feature vectors and runs analytics to augment the features to facilitate efficient GNN-based learning. Then graph querying can be used to prepare the training data for data parallel graph neural network training. For instance, subgraph sampling is a special form of querying. So we need to support efficient querying to quickly prepare the training data sets. Finally, graph machine learning models are trained and used to produce insights about the data. Since the graph itself is partitioned, all these stages should run efficiently in a distributed fashion. Due to the time limit, I won't talk about the details of preprocessing. I just want to point out that graph rewiring is quite important for some problems. For example, we may not want to train the model on the original topology. Instead, we can run a personalized PageRank to compute the most relevant nodes to each node. Then based on the results, we can reconstruct a topology to train the model to produce much higher accuracy. Next, let me briefly talk about graph feature engineering. As I mentioned earlier, the original graph usually doesn't have encoded features, but it does have properties on the nodes and edges. Based on the data type, we encode each property and concatenate the encoded features to form the initial feature vectors. The feature vector only contains local information on each node and edge. So we can run analytics to extract information from the entire graph to augment the features. For instance, we can run Leuven clustering, and as a result, we have a categorical value for each node to represent the cluster it belongs to. We can add such values to the feature vectors. There are also other analytics routines we can use, like PageRank and graph-late counting for feature augmentation. Our distributed system is highly optimized for analytics. So feature augmentation can finish in just seconds, even for large graphs. We did extensive benchmarking to compare our analytics library with other graph products. On a single machine, we are about 1 or 2 orders of magnitude faster for some analytics routines on 2 publicly available graphs. On 8 machines, the system has almost linear scaling. If you are interested in more details, please reach out to me. Next, I'd like to talk about GNN training. Most real-world graphs are quite large with billions of nodes and edges. So full batch training is either infeasible or quite slow. The most popular approach is mini batch training. The basic idea is quite straightforward. Given the seed nodes in a mini batch, we sample a constant number of their in-neighbors for each node. The sampled nodes become the seed nodes for the next round of sampling. In this example, we start from seed node F. We sample 2 of its in-neighbors, A and G. Then we sample A and G's in-neighbors. We can either construct a so-called message flow graph based on the sampling results, or simply treat the sampled nodes and edges as a subgraph. We then leverage our communication and parallel computation engine to do distributed sampling like this, and construct sample subgraphs on each machine. We then perform data parallel training with a given GNN architecture. We found that mini batch training is often not bottlenecked by the forward and backward passes. Partitioning and sampling can incur much more overhead than training itself. For example, we used dist DGL, a very popular system to do large-scale GNN training, to train a 3-layer graph stage model on the largest graph from the open graph benchmark competition using a cluster of 8 machines. You see that partitioning and sampling happen on the CPUs, and they are actually the bottleneck for training. So by the way, the training itself happens on the GPUs, and it is pretty fast. So more than 80% of the time is spent on just the data preparation. Our system heavily optimizes the first 2 stages, partitioning plus data loading and sampling. And we can outperform this DGL by more than 2 times. So here I want to point out that to implement a high-performance graph AI system, we should not just focus on training, right? We should implement a graph data-centric platform that can take care of all the important stages in the entire pipeline. We successfully used the GNNs with mini-batch training on multiple fintech applications like fraud detection. I just want to mention that our customers do care about the latency for both training and inference. And it's convenient to have one single system to perform feature preparation, feature augmentation through some kind of analytics routines and distributed training. We also noticed that GNNs trained with mini-batch training is quite useful. So they can significantly improve the prediction accuracy compared to some baseline models like MLP. Next, I will talk about how graph querying empowers graph machine learning. Most real-world graphs are heterogeneous with various node and edge types and properties. So training certain models may not need all the data. So querying is a powerful way to extract data needed by the training pipeline. For example, one of our customers has biomedical graphs, which contains information about proteins, small compounds, assays, and so on. For simplicity, in this example, I just showed two kinds of nodes. The blue nodes represent proteins, and the pink nodes represent small molecules. An edge between the molecule and a protein means they interact with each other in some way. For training a model to predict drug-protein interaction, we only need to extract the target protein and its connected molecules, which can be done through an OpenCipher query. What this query means is that the user only cares about two proteins and their interacting molecules. The user would like to extract the corresponding two subgraphs. Our system automatically places the two subgraphs on two different machines and activates the corresponding training pipelines. We have an interesting use case for this pipeline to do molecular property prediction. Traditional graph neural network-based approaches treat every molecule as a small individual graph. The prediction task is formulated as a graph classification problem. We found that they may not produce high accuracy. So we developed a new approach in which we construct a similarity graph where nodes represent the extracted molecules or small compounds, and the edges represent their similarity relationships. So two nodes are connected if their Tanimoto similarity coefficient is larger than a threshold. We then formulated the problem as a node classification problem. By the way, we submitted the model to the TDC competition, Therapeutics Data Commons competition, which is organized by a group of researchers from Harvard, MIT, and Stanford. Our model has the largest number of leading entries. To support such domain-specific use cases, our platform runs user-defined functions in Python, which can invoke third-party Python libraries. For example, given the extracted training data represented in this table, the system can run RDKit library, which is the most popular cheminformatics library, to generate fingerprints for the molecules. Based on the fingerprints, the system can construct similarity graphs. Then the function uses PyTorch geometric to train GNNs on the similarity graphs for molecular property prediction. I'll summarize my talk with several takeaways. Large-scale real-world graph learning requires a comprehensive high-performance graph computing platform. It should support all kinds of graph computing workloads like querying, analytics, and graph machine learning in a systematic manner. And all these kinds of computations should run efficiently in a distributed and parallel fashion on the platform. End-to-end mini-batch training is the most popular approach to dealing with large-scale graph machine learning. every stage should be optimized for optimal performance because the customers care about the latency for both training and inference. Moreover, interoperability really matters for a graph AI system to be easily used for specific domains because data scientists in these domains would like to use their familiar tools, and these tools should be integrated into the platform. So finally, I'd like to mention that Katana Graph is certified as a great place to work according to employee surveys. If you are interested in democratizing large-scale graph AI and machine learning, please consider joining us. Thank you for your time.